together here for number 3. But I do want to point out here, and this is actually a homework question you're going to have in the homework with the same numbers in the graph and everything, and we might answer partially here. But notice here that we give you a snapshot of a wave traveling on a rope. That's part A there. So that's just what the wave actually really looks like. If I took a rope and I did that, it's going to have that pattern right there. Okay. Graph B there is actually the mathematical description of that wave for the position as a function of time of a point on the rope. Remember, if it's a transverse wave, a point on the rope is going up and down. But the wave is actually taking this whole path like this. Notice your axes here. You have one. This is just what the wave looks like. Okay, and this is x in centimeters for the wave propagating that way, and this is y. And the wave actually travels to the right. The other graph is a graph of position versus time that does something like this. If I ask you for the amplitude of this traveling wave, which graph can we learn that from? The amplitude is right up here at 15 centimeters, I think. We can see the amplitude of the wave here. This was the position of a point on that rope or the wave with respect to time. And that point was just going up and down. Okay? That was a point here oscillating up and down like this, okay, which wasn't labeled up here for us on that axis. So we can get the amplitude from that right there. Okay. If we want to find the wave speed, we need to do V is equal to wavelength times frequency. Okay? How do we get the wavelength? From which graph here? The first graph. And here's what you need to make sure you're paying attention to. This is a time axis down here. When I'm looking at a full wave, I could say that is a wavelength. This is a full wavelength. But what I actually measure on this axis is time over here, not the wavelength in meters. So be very careful. You can think about this as a full wave. And from here to here would be a wavelength. The actual numbers that I read from the graph, whether I can call that a wavelength or a period is going to depend on what you have on your axis down here. That's why you have two different graphs here. Here, I can go from here to here. And definitely mark this on your graph. This is lambda here in centimeters, so I can read that from this graph. Over here, this is representing the distance here between one full wave. You might also want to call that lambda, but on a t-axis, you would call this t, period, capital T here, where over here, the full wave from here to here is lambda, and over there is period. You guys see the difference there with why I've called this a lambda, and over here I've called this a t? They both represent a full wave, but we're either looking at the mathematical description of the wave here, or we're looking at a snapshot of the real wave on a string right here. That's the difference between when you can call it the wavelength or period. But both of them represent one full cycle. And whether you measure that in terms of wavelength or period depends on really what you have on your horizontal and vertical axes. Does that make sense? So once you know those things, you guys will be able to finish this up. For that homework question, you can find the wave speed once you have the wavelength and the frequency. Let me keep you for a few extra minutes just so I can talk about this last problem. Or are we, I don't know what time it is. Are we supposed to be out of here now?
It's 10:15.
It's 10:15. What time are we supposed to be out of here?
10:20.
Okay, so I'll keep you for a few minutes, maybe over, and we'll talk about one more here. We can stay all day if you want.
No, it's 10:17. Sorry, my watch is.
Okay. Well, either way, let's talk about this last problem with the submarine. It's a quick one on wave speed. And just one thing here about an echo, really. We have a submarine here. And here's my submarine. Okay. You guys have been drawing fish before? There were your fish. So now you can put all your fish into here, and you can really call them fish now and make them that way. But basically, we have a submarine here sending sound down to the ocean floor. And it reflects off, and that's how you hear an echo, is the reflection of sound here off of the floor. And in this case, we tell you we produce a certain sound with a frequency of some number here. We have a frequency here of 2.5 megahertz. That capital M is a megahertz here. So you have 2.5 megahertz. Anybody remember what the stands for here, or what number, what power of 10 that is? 10 to something? You're all right with that part. 10 to something. Yeah, I've seen answers on tests before where they'll write a definition and then it'll say this, and then something, something, something.
They'll write in something.
Yeah, I've actually seen that written down. This is, like for these definitions, sometimes you forget the definition. This is a wave on a string, something, something, something. It gets a happy face, but doesn't get any points. This is 10 to the 6th hertz there for our frequency. Okay. We're going to send that sound down, and we hear the echo 10 seconds later. So it basically takes 10 seconds for the sound to travel down this way. And right now, we're not really talking about all the properties of sound. It's going to travel at different speeds in a different medium, water or air, something different. But we're just assuming here, let your sound travel down, reflect straight back up in a straight line like that. But it's not like just a particle that's going down. It actually has waves that we would show differently. But in terms of looking at it like this, we're just saying the sound's going to travel from here to the ground, or the seafloor here, reflect back up. It takes 10 seconds to do that. Okay, so our time is 10 seconds here to hear that sound, to hear the echo. Okay. We're looking here for how deep is the ocean at that point. Let's just call this y. We know how fast, or we can figure out how fast the wave is traveling, the sound is traveling here. And because we know the wavelength, which I didn't write it down yet, but we can figure out how fast it's going. Your wavelength here is that number that is 4.8 times 10 to the minus 4, right? But we should be able to figure out how fast it's going, right? If we know these two things, the wavelength and the frequency. So if you know that V is equal to lambda times frequency, we have both of those things. Convert your frequency into hertz instead of megahertz like we did here. But that can give us the speed of sound in the water here. Okay. How do I relate the speed of something to how far it's traveling?
Distance over time.
Only when we're not accelerating. Right, so for the very simple case, when we're not accelerating, we can use that because that's our units of meters over seconds. But a lot of you have made mistakes before where you'll just use things like that in a case where you have an acceleration, and that just won't work. So I'm going to write down one of our kinematics equations just to remind us where it's coming from. But as long as we're not accelerating, we can say that distance is equal to velocity times time. I mean, some of you made this mistake on the exam with one of the kinematics problems where you just said that you could do distance over time or angular distance over time to find omega or something. And that's not going to work if you're accelerating. And I think one of them was spinning a basketball around on a finger and there was an acceleration. And if you use something like that, just distance over time to find something, maybe your theta or your omega or whatever, then that's not going to work when there is an acceleration. So the very simple case like this that we have here, we can say distance is velocity times time, or our velocity is distance over time. Okay, so just be careful with those kinds of relationships when you use that simple case or not. Okay, we have that here. You're going to have on the homework where you have a bat or a dolphin or something using echolocation, and it'll be a very similar kind of echo problem, okay, where you'll need to relate the speed, which will be given by our wave speed equation, to distance or time or something. But they aren't going to be anything more complicated than this relationship right here. We're not going to have an accelerating sound wave for your problem. So that's one old thing that we have to remember. It is that simple case with no A, but there won't be anything else in there with kinematics, other than that just very simple relationship here. So if velocity is distance over time, when there's no acceleration, how far does this sound wave travel in 10 seconds in terms of y, the variable that we used over here? How far does it travel? 2y, because we're going to send out the sound here, goes down here, reflects, comes back, so it travels a distance of 2y. So I have 2y over t is equal to wavelength times frequency, because my v is just distance over time here. And we can just solve this for the y, because that's what we're looking for here. Lambda f times t over 2. You could have plugged in numbers separately if you wanted to first find the wave speed and then say that speed is equal to the 2y over time. But I'll just put it all in right here. Plug in the wavelength, 4.8 times 10 to the minus 4. You have a frequency of 2.5 times 10 to the 6 hertz. Our time is 10 seconds. Divide all that by 2. Remember, the hertz is 1 over seconds, so we'll see that the seconds cancel out with the seconds on our time. And we'll be left with just something in meters here. And you get 6,000 meters here for that depth of the ocean here at that point. So I wrote down the kinematics equations to remind you that that's where they come from when there is no acceleration. That's why we can use that simple equation that we did here. But really, I mean, you also remember that speed is equal to distance over time. That's the simple relationship you're using here with sound. We're not going back and doing anything too crazy with kinematics. We will talk a little bit about, I mean, I've mentioned the spring here and the spring force, but we get pretty far away from the topics that we were doing in the first 4 units. With all those forces and accelerations and energy, we will still discuss forces and energy sometimes, but really we won't see many of those equations at all in this current unit. We haven't done much math today. How many equations did I give you today? Which ones? Yeah, basically just this, and I mean I reminded you of the spring force equation from Hooke's law. That's why I'm saying this homework really, there's not much math, there aren't any that you're solving problems. It's do you understand the periods, the frequencies, the wavelengths. Get that started, you can probably finish it up pretty quick if you come by office hours. I think a lot of you can get it done in the next couple of hours. That is due on Tuesday. And just make sure you're remembering some of those definitions and some of those multiple choice questions, remind you of those. But start reading ahead maybe to standing waves on a string. That's what we're getting to next week. Or start thinking about your lab that you need to set up. You've got plenty of stuff to work on, but this definitely won't take as much time. There's a couple extra practice problems, but you might actually have some free time from physics this weekend unless you're really trying to get ahead. This, I don't think will take you that long.